Hello everyone, welcome to my presentation. And my name is Mpao, and I'm going to talk to you about honeypots, that is deception in dynamic web application honeypots. So now, imagine a situation whereby you set a trap and your victims can actually clearly see that this trap is set for them. Will it serve its purpose? The answer to that most probably will be no. It won't serve the purpose. And that's what this research is trying to uh, find out and come up with the solutions. So now, what is a honeypot? A honeypot is any security resource whose value lies in being probed, attacked, and compromised. Like for example, if you put a coin in an open space and see who is going to steal that coin, you're actually setting a honeypot using that coin. So there are different types of honeypots. They can either be categorized into purpose or level of interaction with the attacker. In terms of purpose, a research honeypot is the one that is mostly used by researchers to learn about the attack methods, while a production honeypot is the one that mostly, when you talk about honeypots, people think of. They are used in organizations sometimes to even to deflect away attacks from the most important resources in the organization. And in terms of level of interaction, they can either be low interaction honeypots, and those are those honeypots that actually emulate certain services of an application, not everything, but just a few services of an application. And then medium interaction honeypots are those that are more complex than low level, low interaction honeypots, but they don't give the full operating system to interact with, unlike the high interaction honeypots, which actually give the actual operating system to interact with the attack. So now, what brought the idea behind this research is because of the statistics. Of all the total attacks on the internet, 60% of them were directed towards web applications. And within this period, 2015 up to 2018, web applications were attacked 40 times more than any other attacks on the internet. And within the same period again, CMS were attacked 3 times more than any other application, while WordPress was attacked 7 times more than any other CMS. So in an effort to try to learn about how these attacks operate in the web and the kind of techniques they employ, honeypot technology was introduced. And if we talk of examples of web application honeypots, there is a high interaction honeypot analysis toolkit. There's Dishard, Google Hack honeypot, PHP honeypot. Almost all of these honeypots were designed by one organization called the HoneyNet Project, which was the pioneer in terms of honeypot production. Some other honeypots came after this organization started developing several other honeypots, which we see today. And if you look at all these honeypots, they have one thing in common: they're static. And this static limitation has also led to the development of another type of honeypot, which are called adaptive and intelligent honeypots. That's the kind of honeypots that can actually learn and adapt to any environment they are deployed in. So now, as these adaptive and intelligent honeypots are developed, we realize that there's still another problem that comes with them. And this problem is deception. Most of these honeypots are not deceptive. And this problem also was acknowledged by ENISA, that the current dynamic web application honeypots are not directed much at deception to defeat the attacker in the tactical sense, but rather they are, uh, unlike most historic honeypots, the creators of this honeypots were dedicated more at learning about the tools, the tactics, the motives for the Black Hat community, and sharing the lessons learned. So now we took this research in order to come up with ways of developing a perfect web application honeypot. A perfect web application honeypot, in the sense, we mean the honeypot that is totally deceptive and can do its job without being detected. So we approach this research in this manner. We took one web application that was existing at that moment, and there was only one existing adaptive and intelligent honeypot, which was Glassstop, and then we analyzed it to see where are the problems with the honeypot, and then after analyzing, we tried to redesign the honeypot in order to develop that perfect honeypot, and then after that, we came up with ways of making sure that the honeypot can actually be relevant in the long run. And if you look at this setup here, somewhere in the middle there, if we manage to come up with all these designs, identify, design, and then make sure that it becomes relevant for the long run, somewhere in the middle there, we will be able to come up with that perfect honeypot that we are all looking for. And we employed two theories in order to come up with that perfect honeypot: the interpersonal deception theory and the decision theory. Interpersonal deception theory actually says deception needs to be examined from the context of interpersonal encounters. Like if you talk to somebody face to face, how can you be deceptive when you're talking to that person? It's actually saying it's an attempt to explain deception, or how deception is perceived when two individuals are engaged in a communication. And then we also use decision theory as a way to explain how an attacker can actually be persuaded to take a certain decision over another decision that will be more helpful in designing the perfect honeypot. And the interpersonal deception theory, we actually took only, for the purpose of this presentation, we just took only two propositions there that are more relevant to our research. And that's proposition 12 and proposition 13. Proposition 12 says receivers are less likely to view senders as credible when the sender's communication patterns deviate away from the known expected communication patterns. And proposition 13 says receivers are more likely to spot a deception when the sender's communication pattern deviates from the expected patterns, when receivers are familiar with the sender's information and behavior, and when the receivers have strong decoding skills. Like, for example, if the attacker is a well-skilled attacker and he knows that this kind of system I'm attacking is supposed to behave in this manner, and then the communication pattern of that system deviates away from what is expected, the attacker is more likely to spot deception in this manner, because the communication patterns are deviating away from what he expects the system to behave. And then in terms of decision theory, one can either use the Minimax theorem, which is the crucial theorem, like when the attacker makes a decision to attack a system. How does he make that decision? What motivates the attacker to make that decision? Or the Maximax theorem, which actually the optimistic approach, like believing that everything is fine. Or you can either use the expected utility theorem, which actually quantifies the reason behind making a decision. Uh, in the interest of time, I will not talk much about the decision theorems, but if you want to learn more, I can actually share more about that theory. So now, this table that you see here is a summary of how everything were expected, the expected communications patterns, and then the communication pattern from the reception system, and then the communication patterns after our redesigning of the reception system. So in terms of performance, the honeypot is actually trying to emulate different types of observers, like for example, Apache, Nginx, IIS. And then in terms of performance, you will find that Apache can actually handle 10,000 HTTP requests per second, while Nginx can actually process 20,000 HTTP requests per second. IIS can process 50,000 HTTP requests per second. But if you look at the performance of the reception system, you'll find that it can only process 6 HTTP requests per second. So this means there's a clear deviation of communication patterns from the known or the expected, because the emulated ranges between 10,000 and 50,000, while the reception systems can only process 6. So now, after our redesigning of the system, you can find that the reception system now, or the honeypot, can actually process at least 17,541 HTTP requests per second, which is within the range of the performance of the emulated system. And now we can actually say there's no deviation away from expected or the known communication patterns. And then the emulated systems, the servers, they always obey the search engine optimization rules. Like for example, rendering static files, obeying web quality elements, but the reception system doesn't obey the search engine optimization rules. It doesn't render static files. It doesn't obey the web quality elements. And clearly, there's a deviation away from the known or the expected communication patterns. And then after our redesigning of this reception system, the honeypot now obeys the search engine optimization rules. So now, if you would like to use the Euclidean similarity index based on this results that you got, you can actually agree with me that the similarity index is closer to 1 after our redesign of the system, and it's closer to 0 before our redesign of the system, which means deception system after our redesign is more deceptive than before. So how did we get to all those results? On performance, one way of getting a better performance closer to the production servers is to deploy the honeypot with the production server. And this means the production server will do its purpose of rendering static files, while the honeypot will do only the honeypot scripts, the dynamic scripts or the adaptive scripts. So for you to be able to deploy the honeypot with the production server, 2 scripts are mostly important: the application callable script and the runner script. By default, any WSGI compliant web server, when it's deployed, it looks for application callable script, which is mostly named as application.py or app.py. So if your application doesn't have that application callable script, it will not work with the production server, and the runner script will also look for that application callable script in the server. Therefore, if it's not available there, the honeypot will not be able to be deployed within the production server. Therefore, in our case study honeypot, which is Glassstop, the application callable script is named as wsgi.wrapper. So it means if you want to deploy the honeypot in the production server, you need to rename or redevelop that script to be application.py or app.py, and therefore the runner script will look for that script to be able to function in the production server. And then another way of getting the results that we got is creating a router for the honeypot. A router is actually a script that maps static files to the routes where they are needed. Like for example, because the honeypot does not render static files, it does not render static files because it can't find them where they are located. So if you create a router, you're actually telling the honeypot where to find static files to be rendered. So one way of making sure that your honeypot obeys the search engine optimization rules is to create a router for that honeypot so that it can be able to see where to find static files in your application. If you have deployed your application or your honeypot or your deception system with a production server, this is what happens. The web server or the production server will do the intended purpose of processing static files, handling requests, and responding to the client, which is the browser, or where they are needed at the browser. And then the WSGI, which is the interface between the application and the production server, will do its own purpose of interfacing the production server with the application. And therefore, the honeypot will do its purpose of generating scripts, the honeypot scripts, and then giving the response to the production server. By doing so, it means the honeypot is no longer going to process requests, but they will be processed by the production server, and the production server, because it's faster as compared to the application, and the performance of the whole system will be more in the same level with the production server as compared to when the application or the honeypot is running alone. And that's why there was only 6 HTTP requests per second that were processed when the application is running alone, and there's over 17,000 HTTP requests when they are paired together. So it means that the production server saves times to the application, to the honeypot, by processing requests and then only forwarding the template scripts or the dynamic scripts to the application. So the honeypot will only process dynamic scripts, while any other requests are handled by the production server. So by doing so, the whole system becomes much faster as compared to when the application is supposed to render static files, process requests, and then send the response to the client. So now, because this research, its whole purpose was to be deceptive, behave like a normal system. There is a paradox that we encountered through this research, and this is how it happens. For you to say the system is deceptive enough. It means there's a certain level or there's a certain there's a certain required level of deception that can be classified as enough deception. But now deception is subjective. It cannot be quantified. It's like measuring knowledge. When you say something is deceptive, deception is subjective because it depends on who is the attacker, what kind of knowledge does the attacker has, how does he understand the system. So now, because deception is not quantifiable, how can you say this deception is enough, or the minimum requirement deception that is required for the system to be said this is deceptive? So it's an issue of saying subjective over objective measures. So when we say we are taking this research further, we want to find a way of saying, because deception is subjective, how can we make it objective and agree on the objectivity of this deception? And then if we agree on the objectivity of deception, what amount of deception or minimum deception is required for the system to be said is deceptive? And therefore, if we agree on the minimum amount of deception or the minimum level of deception, it's easy for one to say, my deception or my system has reached this minimum deception, therefore it can be classified as deceptive system. So for you to be able to design a perfect deception, how much is needed of that deception to be minimum deception? So it becomes a paradox there, and we're trying to use the condensate paradox theorem to define how much deception can be said is enough, or how much deception can be said is not enough to be classified as deceptive. So it's an ongoing research which we assume in the near future will provide an answer for this paradox. Thank you so much. Any questions, you can forward me the questions, or you can ask now. I'll be happy to answer your questions. Thank you.